My side of the pond. She's at Queen's University of Belfast, and she'll talk about groupoids and analysis and algebra.
Thank you. I would like to thank also the organizer for inviting me here, and then also thanks for everybody who is sitting here listening to my talk. And yeah, so today I'm going to talk about groupoids, and then quite a few concepts have been already mentioned yesterday by Elizabeth and also by Sarah this morning. And my talk will focus a lot on the Cartan subalgebra, but I'm going to show you how it appeared in analysis aspect and also in algebraic aspect. And this work has been a project going on with several colleagues in the past years. And then I only list here my cooperator, which mainly appeared in one of our recent papers, but you will see the full list in the final slide. All right, so I guess, yes, as I say, Elizabeth yesterday already mentioned what the groupoid is, but I would just like to recap it so that if any of you is not familiar with this notion, at least, here is the definition, and also for me to fix the notation I'm going to use. So for my talk, I will denote by this capital G being a groupoid. And then as Elizabeth said yesterday that, as a groupoid, you cannot always just compose two elements. That's how we talk about composable pair. I denote by this G squared. And then, then in the groupoids, we have this inverse, can just send any element gamma to its own inverse, and then satisfy the following conditions. So basically, if you have composed pair, and then it's associable with another composed pair, and you take double the inverse, you return to the original element, so on. And then what is the other important notion I need is that, of course, once we have element from the groupoid, we can define the so-called source map and the range map, and then basically you just compose those gamma with gamma inverse or gamma inverse with gamma itself. And then another important notion we need for our purpose is that there is a unit space of the groupoid. Basically, it's just the image of the source map of the groupoid, or is coincide with the range map of the groupoid. And then I will denote by this G naught as a unit space of the groupoid. So this is just a recap of the definition. And then for my talk also, I'm going to look into groupoids with various property. I just want to emphasize that during my talk, I'm only talk about Hausdorff groupoids. I know that Elias is going to talk about non-Hausdorff one, but I'm only going to focus on the Hausdorff one, okay? And apart from groupoid being Hausdorff, and then as I say, we are going to focus on the following property. Delta has been mentioned also yesterday by Elizabeth, and simply means that the range map, or equivalently the source map, is going to be a local homeomorphism. And then other two properties of groupoid one can study or one can assume or work on is that a groupoid can be ample, simply means that it has a base of the compact open bisections, and then bisections is going to play a very important role in our work. That's how I'm going to just briefly talk about what a bisection means. So a subset of the groupoid is called bisection if there's an open subset of the groupoid such that we are sitting inside this contain the so-called bisection I start with, and such that when I restricted the source map and range map, there is a homeomorphism onto the open subset of the groupoid. Okay, so that's bisections we are going to work with a lot. And basically, you can think of, when we think of a bisection, basically, this just means that when we restricted our source map and range map, it's going to be a homeomorphism. And then an extra property one can study on the groupoid is called effective, and this means that when we look into the interior of the isotropy of the groupoid, that is the entire unit space, right? Yeah. And then again, just some quick remark, for people who are not so familiar with groupoid. So just a quick remark that if the groupoid is delta itself, then we know that the unit space is an open set. And then moreover, when we look into the inverse of the source map of any element, we denote by this Gx. And then similarly, we can look into the inverse of the range map and then lay out discrete in the groupoid, no matter what element we pick up from the unit space. And then on the other hand, we can also see that if G is delta, then in that case, this is equivalent to say that the groupoid itself have a basis of open bisections. So as you can see that once we work with delta groupoid, then in that case, those open bisections actually can form a basis of the groupoid. And then secondly, as I say, there are various properties we can assume for the groupoid. So now if on the top of delta groupoid, moreover, if the groupoid is umbel, then this means that when we look into the unit space G, then this unit space is actually a totally disconnected topological space. The last one is just a quick remark. When we look into the delta groupoid, if it's Hausdorff, this, as I said, my assumption, then we know this equivalent to say that the unit space is a closed subset. All right, and as I said in the beginning, I'm going to focus a lot on the groupoid and how it appeared in the analysis aspect and the algebraic aspect, and I'm going to focus a lot on the Cartan subalgebra. And then this, what Cartan pair or Cartan subalgebra has appeared already in several talks, but I will just recap it here also for my purpose. And yeah, so I think both Sarah and Elizabeth mentioned already, Cartan pair in sister algebra has been given by Renault in 2008. This is the one I cite here. And then I just quickly record the definition. I just write in short. So if there's a pair A and B, they are both sister algebra, and then we call this pair is a Cartan pair, or we say that the subalgebra B is a Cartan subalgebra of the larger sister algebra A. If the following conditions satisfied, this simply means that B is a maximum abelian subalgebra of the larger algebra A, and moreover, A contains the approximation identity. And then here I say the subalgebra B is regular in A. This is the same thing to say that when we look at the normalizer of B, which generates the whole big algebra A. Okay, this is what we see in the morning. And then moreover, of course, there is a faithful conditional expectation from A until the subalgebra B. Okay, that's just what I've been repeating. And then this also has been said several times. Not only we can talk about what means by a Cartan subalgebra of a sister algebra A. Moreover, we know this was a result by Renault that every Cartan pair can actually be realized by a twist groupoid sister algebra. So in the sense, the groupoid can be constructed, the twist can also be constructed. And not only that, there is already one-to-one correspondence. This simply means that, yeah, once if you construct those groupoid and twist, they are uniquely determined. Okay, yeah. I'm going to go back to this in more detail later, but let me just move on. So I just want to recap what means by a twist sister algebra, and then later I'm going to move to the algebraic side of that, and that's how, in order to be able for me to show you how can I compare these two setup, and then I would like to also go through how a twist groupoid sister algebra can be defined. And instead of the twist Elizabeth used by using a two-core cycle, I'm going to take a different type of more general twist, which was defined and given by Conjon in 1986. Okay, so the notation may look a little bit different. All right, so now if I start with delta groupoid G, then the twist I'm going to use here, as I say, is defined given by Conjon, and I would say a twist of a groupoid I would denote in this way. This sigma is actually larger groupoid, and then I have two map I and Q, and which is a locally split extension of the original groupoid G by this unit space closed unit circle, and this extension is through this exact sequence. I'm going to show you the detail in next slide, and then moreover, this show exact sequence will satisfy certain conditions. So this simply means that when we look into the image of this, say, unit space, and through the map I, that will be central in this larger groupoid in the middle in this short exact sequence. And what central means simply means that if we take into account the image of this map I with a range and source map that is kind of commuting the way with the element, And then to be more precise, what means by this, what exactly this twist means, the full definition is listed below. I'm not going to go through details, but just quickly, briefly saying that. So apart from we have this short exact sequence, Then as I say, the middle one, this can be seen as an extension of the groupoid G, and then sigma itself is also a groupoid. Moreover, when we look into the unit space of this larger groupoid, this is coincide with the image of the group unit space from the original groupoid G cross the identity element from the unit circle. And then moreover, because this is a short exact sequence, of course, this, yeah. So, and then of course, in that case, we have I and Q, they are both continuous group homomorphism. Moreover, when we restrict it to the unit space, they are just homeomorphisms. And satisfy various conditions, the exactness, everybody know what that means. And then the centralness I have mentioned already in the previous slide. And one extra definition is that the groupoid sigma is locally trivial, G bundle. And then what that means simply means that we will be able to find these so-called open bisections on the original groupoid G, and then such that we can also associate a continuous map on these bisections, map back to this bigger groupoid, such that when you compose this Q map with this continuous map P A, then let's return to the identity on the bisections. So basically, that's what means by a local trivial bundle means. Okay. And yeah, this definition look rather complicated, but if you prefer a continuous two-core cycle, then you can just take your two-core cycle, and then it will give rise example of such more general twist on the groupoid. Okay. All right, and then just a quick example. If we just take a Cartesian product of the groupoid G and cross with unit circle, of course, this can be viewed as a twist over G, and then it's just a trivial twist. Okay, that's an easy example. Secondly, as I just mentioned quickly, you can just work with or pick up a continuous two-core cycle if you like, and then yeah, in that case, of course, the new product can be defined by the original one, just take into account of the value of the cocycle. And similarly, the inverse of this G cross T can be just simply defined by cooperating with the cocycle, the value of from the cocycle as well. Okay, so this is what I mean. You can actually check easily that once you start with a continuous two-core cycle, then you can actually define the groupoid product and the groupoid inverse quite easily, and then you can check easily that definitely this G cross T incorporating with the two-core cycle definitely give rise extension, local split extension of the original groupoid G. Okay, so these are the standard two examples of the twist I have mentioned previously. And so here, this slide is to just quickly recap what means by a twist groupoid system algebra. And now if I start with a locally compact host of alta groupoid, and then this sigma is a twist I have defined previously. In that case, we can, this is my notation to denote the start algebra under the dollar operation. So that is a collection of all the continuous function with compact support on sigma, because sigma is a groupoid itself, of course, it's a topological space. And then we can define the product and also the convolution involution. Okay, so we can define the following way. And then as I say, because we are working with the functions defined on the groupoid element may not always be composable. So that was the reason even when we define such a product, then of course it is only well defined when we work with the composable pair. And then on the other hand, I need the following condition. If I pick up a continuous function, I say this function defined on sigma is T covariant if the following condition satisfied. This simply means that if I take a complex number acting on the groupoid element, then apply my function f on it, then actually this coincides with the value of the function on the groupoid element and add by the conjugate of the complex number coming from the unit circle. Okay. And that's what we say by the T covariant function. And then once we have those T covariant functions, we can define the following set, and I denote by this CCG gamma, gamma. Sorry, it's sigma. And yeah, so what that means, this is just a collection of all the functions coming from the continuous function defined on this larger, well, the twist. This simply means that it's a larger groupoid contain the original 1G with compact support. Moreover, we only collect those continuous functions which are also T coinvariant. Okay, and that's our notation, although it looks a bit weird, but this is a collection of functions have a domain on sigma instead of G itself, right? And then once we have such a continuous function with compact support, of course, we can look into what means by reduced twist groupoid C-star algebra. Basically, just take the closure according to a C-star norm, and then this would give us the reduced groupoid C-star algebra. Okay, and then I just write down precisely what this reduced C-star norm means here. So that's just, it is just a standard approach, I would say. Okay. All right, and this is the reformulation of the Cartan pair I have shown previously. And if you look into the condition here, it looks almost the same as the previous one, but the only difference is that previously when we refer to the original Reynolds this Cartan pair or the Cartan subalgebra, there's a condition that A need to contain the approximation identity. But as you can see here, we don't really need that, because it was a result recently by David Pitt, saying that once you have these three conditions, then the approximation identity is automatic by these three conditions. So in the sense, the original Cartan pair or Cartan subalgebra conditions can be reduced just by simply asking these three conditions. Okay. And here I also note down this the regularity I was mentioned previously. Basically, when you look into the linear span of the normalizer of the subalgebra, this really generates the whole bigger C-star algebra A. Okay. And then what this result has mentioned a lot, and then I just repeat it here so that I can compare to the algebraic side later on. And say that it was a result by Renault in 2008, but recently there's a revised or generated version which get rid of the condition being separable. So in a sense, even in the non-separable case, Renault's results still hold, right? So it says that if there's a twist over effective locally compact host of alta groupoid, then in that case, definitely when we look into the reduced twist groupoid C-star algebra, and with the subalgebra, which is just a collection of all the continuous function vanish affinity on the unit space, this indeed gives rise a Cartan pair. So simply says that this subalgebra is a Cartan subalgebra of the reduced groupoid C-star algebra. Okay. And not only that, as I said previously, once we start a Cartan pair, then we can always construct such a twist over an effective locally compact host of alta groupoid. So simply means that we can really just work with the normalizer of the subalgebra B and then construct what will be the twist sigma. And then once we have the twist sigma, we can take a sensible quotient to get the groupoid G. Okay, then just need to check the groupoid G indeed satisfy the effective and then also the being housed of and also being alta. Right? But it's constructible. All right, so now I'm going to move to the algebraic side. And then, so original idea, we try to mimic what has been seen in the C-star setup, right? And then, but we want to temporarily forget about the C-star condition, just looking to the algebraic ring theoretical definition and then ideas, right? So what says here, now I just want to distinguish my notation. That's why I denote by A0 and B0. The 0, the not here doesn't mean anything, all right? So I denote by this A not being a algebra over a complex number, and then this B not just being a commutative subalgebra of A, right? And then as you can see, the condition is actually very similar to the previous, Cartan, the standard C-star Cartan condition. The only difference is that now, when we look into this regular condition, because now we only consider the algebraic structure, we don't have the start, like the start operation from C-star algebra. That was the reason the normalizer need to be revised a little bit, okay? So we still have the regularity. This means that my larger algebra still can be a span of the normalizer. And then we also have the fastful conditional expectation. And then another difference is that now when we look into this B0, the subalgebra, still being a maximum abelian subalgebra of A0, but we ask that this B0 is actually spanned by the idempotent of the algebra, okay? And then in order to mimic the approximation identity, we ask also the set of the idempotent, that's my notation, form a set of local units of the big algebra, right? Yeah, so you see that the condition is actually very similar from the original C star setup. And then, so we define that, calling that this pair is the algebraic Cartan pair, okay? And then what we show is that, I will explain detail later, but what we show here is that now, again, if I start with a twist over an elbow, if I just relax a little bit of condition, if I look into a Groupoid G, which is again Hausdorff and delta to start with, and then we can always, as I said previously, we can pick up a twist over such a Groupoid. And what we can show is that now, if G is again an effective Groupoid, then in that case, we can actually construct a pair of purely algebraic analog of C-star algebra, which satisfy these algebraic conditions. Okay, I'm going to say more detail what that means, but yeah, as you can see, this is still a paired, and this pair, the bigger algebra we call the twist Steinberg algebra, is again an algebra built up on this larger Groupoid sigma. It's a twist over the original Groupoid G. Then we have a subalgebra. This is going to be a maximum abelian subalgebra sitting inside this larger algebra. And then although this term look rather complicated, but this is just isomorphic to the so-called Steinberg algebra defined on unit space. Okay, I will explain more what this notation means in the next slide. But my purpose just to show you that not only we can just look into the purely algebraic side of the Cartan paired or Cartan subalgebra, then we get the same result if we just forget about the C-star structure, say that way. Okay. All right, so the following slide, I'm going to show you what this twist Steinberg algebra or the standard algebra means. So now if I weak a little bit of the condition of the Groupoid, so we only look in Hausdorff without being effective. And then if B is, I pick up B as a bisection, sorry, it's look a bit confusing like a subalgebra, but now the B stands for the bisection. And then once we pick up a bisection from our Groupoid G, then we can look into this heuristic function or indicator functions defined on the bisection. And then once we have those collection of this heuristic function defined on the bisections, we can just take the span, the linear span of all those heuristic functions, and then and then this gives us an algebra, okay, of G, right? And then once we look into this A of G, we can actually similarly define the product. This is convolution and involution, and then this, as you may recall, this exactly if you think of how the product and the involution and convolution was defined on the C-star algebra. The idea is exactly the same, right? In the sense we can use the same product and to give rise to algebra in this setup. Okay. And so this is algebra. Moreover, one can check that if we take a C-star norm, no matter C-star full norm, full C-star norm or reduced C-star norm, then this algebra is actually dense in CC of G, or dense in the, well, if you take the reduced C-star algebra, then it will be dense in the reduced C-star algebra. Okay. So that's the untwist version, and then I'm going to show the twist version. So what that is again, if I start with twist, now I actually write down a word saying that my twist need to be discrete, because as you may recall that previously when we tried to define the Groupoid, the twist Groupoid C-star algebra, we work with the T covariant functions, right? Now, if I want to similarly, in the sense, eventually, not only I want to define this twist Steinberg algebra, of course, as we see previously, the previous slide, I want this algebra be dense, being a dense subalgebra of the Groupoid C-star algebra, okay? So that's how, of course, we think of taking also the T covariant functions, yeah? But now, without asking this sigma being a twist, or I mean, if you recall how the twist was defined, we take the original groupoid G, and then we take the unit space of the groupoid, and we actually cross the unit circle, right? This gives us part of this exact sequence, yeah? And then now the twist, the discrete twist here simply means that I will equip the unit circle with a discrete topology. And the reason doing so is that unless I take the discrete topology, when we try to look into these T covariant functions and define such an algebra, we may only get the trivial functions. There is no interesting element sitting inside this algebra. Okay, so that's a constraint. We ask to work with a discrete topology for that aspect, right? For that reason, say. So now, so otherwise the definition is very similar to what we have previously. I take a twist and then just ask the topology over T is a discrete topology, and then we can define such a so-called twist Steinberg algebra, and that is just a collection of all the continuous functions, like how we did previously, define on the twist sigma, and then collect those T covariant functions. Moreover, I ask the support need to be compact. Okay. The reason here I write the Q support of F is because now when you look at the support of F, F is a function defined on sigma, right? And then if we want to see what this compactness means, it may not mean anything or much when you look into the support on the sigma itself. And that was the reason we asked that when I map it in by Q map to the groupoid, to the original groupoid G, this needs to be a compact set sitting inside the groupoid G. And yes, just note down that was one of our previous work. I should actually mention. Yes, I would like to mention the name of that. So that was given by Steinberg himself and also Lisa with her co-operator. They are independently work, and Steinberg was looking into more the groupoid algebra itself, and then Lisa's work they do look into this particular notation, function over, have a complex values. And later I'm going to return to Lisa's work and give you example, a concrete example of this Steinberg algebra and the twist Steinberg algebra. All right, and then just some quick remark. As I say, when we define this twist version of the Steinberg algebra, we want to see, in a sense, we want to have a similar structure or property as the non-twist version. So one can check also, once we define such a twist Steinberg algebra, then it's indeed a dense subalgebra when you look into the twist groupoid system algebra, okay? And of course, depending on which node you are working with. Secondly, if we just take the trivial twist, this simply means that if I just take the twist sigma being the original groupoid G cross the unit circle, as I said, I need to equip my unit circle with a discrete topology. In that case, the twist Steinberg algebra is just coincide with the original Steinberg algebra. Okay, there's nothing new. And there are examples of such algebra in the sense it's not empty set. And then example appeared from, one can also look into the discrete group algebra. I forgot to mention previously that of course one can look at the discrete group algebra, then this gives rise to Steinberg algebra as an example. And of course we can look into the twist version of the group algebra, and then that serves as an example of the twist Steinberg algebra. Okay, and there are examples also coming from the K-graph. So in the sense, there's a K-graph algebra serve as an example of if you twist how the K-graph algebra is defined, the higher rank graph, then this also serves an example of the twist Steinberg algebra. Okay, I will say a little bit more later. All right, so example, yes, that's actually referred to one of Lisa's early work with her co-operator. If I start with a direct graph and then with mild condition, this means that the circle has an entrance. And then as we see previously from Sarah's talk, that we can define or we can look into the graph algebra of this direct graph. And although my notation is different from her notation, and this actually gives rise a level path algebra, and they can be defined in various ways. Either you can record what Sarah slide and show you how this graph algebra can be defined. On the other hand, as the discussion between Sarah and George, that there is also Groupoid, a model of that. So in the sense, you can also build up the algebra based on the Groupoid model you have gotten from this direct graph. Okay, one way or another, there is algebra. I denote by this A, C, E. So in a sense, the graph algebra itself is a Belfast algebra, which is actually isomorphic to the Steinberg algebra one can construct from the Groupoid model. Okay, so let me repeat again. Once we start with this direct graph, then one can build up a Groupoid model from it. And once we have a Groupoid, of course, I can just try to follow the previous definition of a Steinberg algebra. Then this gives rise this A, C of E. Okay, and then this Steinberg algebra of a direct graph is actually isomorphic to the Belfast algebra or the graph algebra if you want. Right? Yeah. And on the other hand, Sarah also showing in her slide that there's a commutative subalgebra sitting inside it, and then moreover is maximum abelian. And so if we just pick up this pair, and of course this give rise to algebraic Cartan pair. Okay, yeah. So what I want to say, or I want to convince you, is that yes, those algebraic Cartan pair does exist, and there are examples of that. So next. As we see from various talk that Cartan pair or Cartan subalgebra has been an important topic, and then we work a lot with that. And then we also try to relax various conditions, see whether we can get a weaker version of the Cartan subalgebra. Okay, and then we took a different approach. Our approach is that we try to relax the assumption that the subalgebra being maximum. Our subalgebra will still be abelian, but not a maximum subalgebra. Okay, so what do? I will just show the whole slide. So now, again, I just look into the purely algebraic aspect. Okay, so I start with the algebra over a complex number, and I have a commutative subalgebra. As I say, I just delete the subalgebra to not asking the subalgebra to be maximum. And I still have the other condition, right? I still have the idempotent form a local unit of the big algebra. Then my subalgebra is still being a span of the idempotent. I still have the regularity. And then another modification is that instead of asking we have a phase for conditional expectation, actually we have a specific condition on this conditional expectation. Simply we ask such a function, such a map need to be called implement by idempotent. What that means, it simply means that whenever we apply our conditional expectation on those normalizer, because we know the algebra, the big algebra is really generated by normalizer, right? So of course I can just apply this conditional expectation on the normalizer. And what we ask for is that the image of this of the normalizer under this conditional expectation is just can be written as the normalizer times idempotent element. Okay, and then that's how we call our phase for conditional expectation is implemented by idempotent. Yeah, and we call such a pair A0 and B0 algebraic quasi-Cartan pair. Okay, yeah, and I didn't write it down here, but once we have algebraic Cartan pair, then it definitely satisfies algebraic quasi-Cartan pair. It's a stronger version. In the sense, this quasi-Cartan pair is a weaker version of the original Cartan pair, right? But the question is that we see previously, once we have algebraic Cartan pair, then this can be realized again by this twist Steinberg algebra, right? Or another way around, once we have a pair of a twist Steinberg algebra, it can always give rise to algebraic Cartan pair. So we would like to have a similar result, right? Ask for whether we can also have a Groupoid construction once we have such an algebraic quasi-Cartan pair. Okay, that's the purpose we want to achieve. But we see that in order to do so, we can actually relax the original effectiveness of a Groupoid. We can just work with ample Groupoid, but satisfy another condition, then that will give rise a Groupoid, a pair of, the Groupoid and the twist, which does give us algebraic quasi-Cartan pair. Okay, I will show you the next slide. So I will just briefly say what this extra condition we work with, which kind of realization, well, yes, we can relax the condition on the group itself, not necessary to be effective. Ample will be enough, but nevertheless, we need this extra condition in order to be able to guarantee that the quasi-Cartan pair indeed exists, can be constructed. Okay. So what I mean here by algebraic local bisection hypothesis simply means that it's really a condition on the normalizer. As we see previously, normalizer is really when you look into the normalizer, this gives rise all the algebra, right? The big algebra. So somehow this is really a condition imposed on the normalizer. So this hypothesis simply says that if I pick up any normalizer from my bigger algebra, and then we can look into the open support of this normalizer. Again, I just, in the sense, in order to fit better back to my original Steinberg algebra or twist Steinberg algebra, that's why I still look into just the Q image of my support on the original Groupoid G. Okay. And as long as this open support under the image, under the map Q is an open bisection, so in the sense I want this bisection property. If this is an open bisection on my original Groupoid G, then I call my this twist satisfy this local bisection hypothesis. Okay. And then what we show is that if I start with an algebraic quasi-Cartan pair, in the sense if I start with a pair which is a bit weaker than the original Cartan pair, and then what we can do is that this is equivalent, we will be able to construct a discrete twist over an ample host of Groupoid G, and then moreover satisfy this discrete twist will satisfy our hypothesis such that the pair I start with indeed can be realized by the twist Steinberg algebra and the Steinberg algebra itself. So this is what I was saying previously. That's a goal we want to achieve, that if even we can define a weaker version of the Cartan pair, can we still realize it by twist and a Groupoid, okay, through this Steinberg algebra, through the purely algebraic language, yeah. And then in order to do so, this local bisection hypothesis is actually very essential for us to be able to realize that, okay. All right, and then as in my title, I say that I would like to talk about Groupoid both in analysis in algebra, and up to now I have been talking a lot on the algebraic side. I would like to bring us back to the C-star side. So we define something similar of this local bisection hypothesis, but we move back to the C-star side. Okay, and the difference is now when we look into the hypothesis, let me go back. I basically pick up, it's a condition on the normalizer of my bigger algebra, right? And I want to look into the support, the open support of my normalizer, whether it is open bisection or not, all right? So now if I really want to move back to the C-star setup, of course, in that case, we still have the normalizer from the C-star, the C-star algebra, yeah? So this is what we do. Let me show it full, okay. So what we do is that, again, now I just take the normalizer from the larger C-star algebra. This simply means that if I start with a twist and with a Groupoid, of course we have this reduced Groupoid C-star algebra that will serve as a larger in our pair. Then we have the subalgebra, which is just C0 of the G0. Then now if I take my normalizer, then of course I can again look into the open support of my least normalizer and then again I just care about the support under this Q map. Okay. Just yes, it's N. Thank you, Elizabeth. Thank you. Yes, it's N. Yes, it's normalizer. Yes. And yes, so we just ask exact the same property to see whether this Q, the support under the Q map is an open bisection or not, now under Groupoid, yeah? And then, so basically, just exact the same idea, asking whether the support of the normalizer is open bisection or not. And what we say is that if we again refer or look back Reynolds result, we see that actually this C-star algebraic local bisection hypothesis is automatically satisfied when we have a twist over an effective groupoid. So in a sense, if we start with a groupoid being effective, and then with a twist, then the Cartan pair you have is always automatically satisfy this C-star algebraic local hypothesis, local bisection hypothesis, right? However, the two versions are not the same in the sense, even ideally we look into the support of this normalizer. Nevertheless, we work with the normalizer from the C-star algebra or the normalizer from the twist standard algebra. They are not the same, okay? So I will show you the example and I may finish here. So I just want to show you that until now, when we try to work on the algebraic side, it's very much look like we try to mimic what we know from the C-star algebra side, and then we modify the definition, and then we try to weaken it, and then try to look for different things, nevertheless related to the C-star algebra construction, C-star algebra structure. But what I'm going to show you is that now, even when we define this so-called local bisection hypothesis, when we look into this support of the normalizer, from the twist standard algebra or the twist Groupoid C-star algebra, actually they don't really behave exactly the same. So in the sense, if you recall one of the early results I mentioned, I need this local bisection hypothesis to construct those the algebraic Quasi-Cartan pair, yeah, and that exists in the algebraic setup. So in a sense, I claim that we can define a weaker version of the Cartan subalgebra in the algebraic setup once I have the local bisection hypothesis satisfied. Okay, but what we are going to see is that this weaker version of the Cartan subalgebra only exists in the algebraic setup. When we move back to the C-star setup, this weaker version of how we defined it is just, yeah, it doesn't give anything new. Okay, yeah. So let me go through the example. So I just say a quick example, a statement here that even we just look into the integers, yeah, set of integers. Of course, this is a group. Then of course, group can serve as an example of a groupoid, right? So that is the example I'm going to look into. So what we can see is that the integer itself satisfies the algebraic local bisection hypothesis, but it doesn't satisfy the C-star algebraic local bisection hypothesis. Okay, and then I will just quickly show it, and then I may finish here. So to demonstrate that the group of integers doesn't satisfy the C-star version of the local hypothesis, local bisection hypothesis is actually not too hard to see. So we all know that if now we want to look into the reduced group C-star algebra over there, then this is basically just the continuous function defined on the unit circle T, okay, via the Fourier transform. And then because now I take this set of integers as my groupoid, then the unit space in that case is just the identity, right? Just a zero. Yeah, have a trivial unit space. And so now if I look into what will be the Fourier transform of the subalgebra, I mean this C0 of the G naught, then this is just a collection of all the scalar multiply of the heuristic function, I mean the identity function defined on the circle. Yeah. So that's our image of the C0 of G naught on the Fourier transform. So now if I look into this function, we denote by M defined on the unit circle, and then just define in the following way. That's my function M, okay? And then this is a continuous function defined on the unit circle. Moreover, one can check this function M is indeed a normalizer of the algebra, right? But what we see is that now if I map it, well, in the sense, if I map it by this J map, which I can go back to show you what is J map. If I map, so this J map just a useful tool to, in a sense, help us to write down element from the reduced C-star algebra as a continuous function. All right, yeah. So what we have is that if I look into what will be the preimage of my list function M under the Fourier transform, then we can actually write down this function, this element concretely as the following. Okay. But when we look into this function, then actually it is non-zero on both bisections which contain 1 and 2. Yeah. So because of that, of course, when we want to look into the support of our normalizer, because this M is a normalizer, right? And then when we want to look at this local bisection hypothesis, as I said previously, basically we just care whether the support of the normalizer is an open bisection or not, right? But as we can see here now, when I look into the support of this element really, coming from my normalizer, it's actually supported on both 1 and 2. Yeah, so that's how it failed the C-star algebraic local bisection hypothesis. Okay, yeah, and on the other hand, set of integers will satisfy the algebraic one, and simply because now if we just look into so when we look into the Steinberg algebra of integers, this is just a linear span of the heuristic function anyway, okay? And then when we look into the support of the normalizer from such an algebra, then what we see is that if we look into the intersection of the unit space, that can, I mean, at most the intersection can only have one element. So that was the reason set of integers will definitely satisfy the algebraic version of the local bisection hypothesis. Yeah, so that's the reason. I didn't write down the detail of what I just said, but set of integers satisfy the algebraic version, but not the C-star version. All right, yeah. So I just want to conclude that. Let me show maybe the final slide. So so what I would like to conclude is the following. As I say, right, we try to relax the condition of a Cartan pair by using this algebraic language. But what we can show is that now if we return to the C-star setup, whenever we start with the effective groupoid, then the previous result from Renault, of course, we know that we have this Cartan pair, which just can be realized by the twist and the groupoid. And not only that, we also see that we have a result showing that once we start with the effective groupoid, then for any twist over the groupoid, we actually, in a sense, it does satisfy the local bisection hypothesis. Simply means that if I pick up any normalizer from my C-star algebra, then look into the open support of such a normalizer, then it's always an open bisection. Okay. Not only that, even when we look into the non-twist version, in the sense I can even just forget about the twist over the groupoid. Once I start with effective groupoid, then in that case, we know that it's equivalent to check that every normalizer from the reduced groupoid C-star algebra is, when I look into the open support of it, is always open bisection. So in the sense, we kind of also give rise, not only to show that this weaker version of the Cartan pair coming from the algebraic setup doesn't really appear in the C-star setting. Not only that, we give new equivalent conditions to check whether a groupoid is effective or not. Okay, I guess that's me. And I just list all the relevant definition and paper in here in the last slide. Thank you very much.